Dear classmates, welcome to the VLSI testing class. Today we are going to introduce the first single StaticCE 4 diagnosis technique, the static cause-effect diagnosis. We call this a cause-effect diagnosis, where cause is the fault and the fault effect is recorded in a dictionary. We call this a static diagnosis because the dictionary does not change with our circuit under diagnosis. In static cause-effect diagnosis, we have two important steps. First, we run fault simulation for all the faults. For good diagnosis result, we don't perform fault dropping. And then we generate a complete fault dictionary. In the second step, with simulation failure and the test failure available, we compare SF and TF to generate a diagnosis score so that we can rank the diagnosed fault list. Here is an example of a complete fault dictionary. Consider this circuit with 3 inputs and 2 outputs, 7 and 8. We applied 4 test patterns from pattern 1 to pattern 4. All the good values are shown in this figure. On our left hand side, we have a complete fault dictionary where each row represents a fault. For example, the first row represents the simulation failure for input 1, StaticCE 1 fault. If input 1 is StaticCE 1, we would observe simulation failure at output 7 and 8 for the first pattern, but we will not observe any simulation failure for the second and the third pattern. In the fourth pattern, we would observe 1 simulation failure at output 7, but no simulation failure at output 8. Totally, we have 20 single StaticCE 4 in this circuit. After equivalent fault collapsing, we have 14 faults. In the last row, for example, we have 3 equivalent faults collapsed into a single row. As you can see, this is a very large dictionary, where the dictionary size can be proportional to the number of faults by the number of failing patterns by the number of failing pins. So this is a very large information. To make sure you understand this definition very well, now let's have a simple quiz. Consider the following circuit and the only 3 faults: input A StaticCE 1, J StaticCE 0, and Q StaticCE 1. Let's apply 3 test patterns from P1 to P3. The good outputs are shown as 1, 1, 0. Please fill in the table to generate a fault dictionary. Now please pause the video and work on this quiz. Welcome back. Have you got it correctly? For A StaticCE 1 fault, the simulation failures can be observed in pattern 1 and pattern 2. For J StaticCE 0, the simulation failure can be observed in pattern 3, and there is no simulation failure for Q stuck at 1,4. Now that we have a fault dictionary and we tested the circuit on the tester, so we also have test failure, we can compare simulation failure with our test failure. There are 4 possible outcomes. The first one is TPSP, which is test pass, simulation pass, which means the circuit pass on the tester and also the simulation. Second, TFSF, test fail, simulation fail, which means the circuit fails on the tester and also it fails in the simulator. The third case is TPSF, test pass, simulation fail. That means the circuit passed on the tester, but we see simulation fail in the simulator. And the fourth is TFSP, test fail, simulation pass. According to these 4 categories, we can draw this simple conceptual diagram. In this diagram, the blue circle represents simulation failure, and the red circle represents test failure. We have TFSF in the intersection. Outside of the circles, we have test pass and the simulation pass. Based on these 4 possible outcomes, we can calculate the diagnosis score, which measures the similarity between test failure and the simulation failure. With the diagnosis score, we can then rank the possibility of the diagnosed fault list. Please note that diagnosis scores can be defined by the tool. Now let's return to our example circuit under diagnosis. For this particular circuit, we apply 4 test patterns. The corresponding good outputs and the CUT outputs are shown in this figure. For test pattern number 1, both output 7 and 8 fail the test. For pattern number 2, it's the same. For pattern number 3, both output 7 and 8 pass the test. For pattern number 4, both outputs 7 and 8 fail the test. So we can have test failure like this. Now we can compare the test failure, which is shown in the last row, with the simulation failures. For test pattern number 1, both output 7 and 8 are TFSF. For pattern number 2, both output 7 and 8 are TFSP because we don't have any simulation failure at pattern number 2, given input 1 stuck at 1,4. For pattern number 3, they are TPSP. For pattern number 4, output 7 is TFSF, but output 8 is TFSP. So, given this comparison result, totally we have 3 TFSF and 0 TPSF. Let's define the diagnosis score as 10 times TFS minus TPSF. Given this equation, we can calculate the diagnosis score of this fault to be 30. We can do the same thing for the second fault. Input 2 stuck at 0. For pattern number 1 and 2, they are both TFSP. For pattern number 3, however, they are TPSF because the circuit passed the test on the tester, but we have simulation failure here. For pattern number 4, output 7 is TFSP, output 8 is TFSF. So for these 4, we have 1 TFSF, 2 TPSF. The diagnosis score, according to the equation, is 10 minus 2, which is 8. We can do this calculation for all the other faults in the dictionary. Eventually, we will pick the one with the highest score, which is 40 stuck at 04 here, to be the most likely fault in this diagnosis, and the one with diagnosis score 30 is ranked number 2 in the diagnosed fault list. To make sure that you understand our concept, let's do a quiz. Suppose we have a COT where output is 0, 1, 0. Please calculate the diagnosis score to rank the following 3 candidate faults: A stuck at 1, J stuck at 0, and Q stuck at 1. Please note that the diagnosis score is defined as 10 times TFSF minus TPSF. Now please pause the video and work on this problem. Okay, have you finished? First, let's determine what is our test failure for this particular COD. Because this COD failed the first pattern, so we have 1 X in the first pattern. Now we compare the test failure with 3 simulation failure. For A stuck at 1, this is TFSF. For P2 is TPSF. For P3 is TPSP. So the total score is 10 minus 1, which is 9. For the second fault, J stuck at 0, the first pattern is TFSP. The second pattern is TPSP. The third pattern is TPSF. Based on our equation, the diagnosis score is 0 minus 1, which is minus 1. And eventually, for the third pattern, the diagnosis score is 0. So, overall speaking, A stuck at 1 is ranked higher than the other faults. Besides the previous definition of diagnosis score, we can have also other definition. This is another example. As shown in this figure, the diagnosis score is defined as TFSF over TFSP plus alpha TPSF plus TFSF. This is a number between 0 and 1. Alpha is a small number defined by the user. You might wonder why TPSF is discounted by the factor alpha. This is because test failures are sometimes not fully recorded on the ATE. due to limited ATE memory. So we discount this TPSF by the factor alpha. Here is the same example with the new diagnosis score definition. For the first fault, there are 3 TFSF and 3 TFSP, so the score is 3/6. For the second fault, we have 1 TFS and 2 TPSF, which is in pattern 3, and we have 5 TFSP here. So the score is 1/6.2, where alpha is set to 0.1 in the equation. When you compute all the score for all the faults in the dictionary, 4O stuck at 0, which is here, is ranked as the top 1 fault to be diagnosed, and the other 2 faults are ranked the second in the diagnosed fault list. We can use another diagnosis score definition. In this diagnosis score system, we have 2 scores. The P score is TFSF over TFSF plus TPSF. The M score, the match score, is TFSF over TFSF plus TFSP. Both numbers are between 0 and 1. The higher the score is, the better the match or prediction they are. Given the same circuit and the same test failure, we can calculate the diagnosis score for the circuit. For the first fault, we have 3 TFSF, 0 TPSF, 1 TFSP. The P score is 3/3. M score is 3/4. We can do this for all the other faults in the circuit. Using this dual score system, we can have 4 possible cases. For case 1, both P and M are perfect 100%. This indicates a perfect match where TF is exactly the same as SF. If we see this case, we can say that a single stockhead fault is perfectly diagnosed. For case B, we see a perfect P score 100%, but the M score is less than 100%. This figure shows that the TFSP is non-empty. One possible explanation for this case is multiple stockhead fault, where there is a second fault that should be diagnosed. For case C, the P score is smaller than 100% and the M score is 100%. We can see from this figure that TPSF is non-empty. One possible example is a stuck open fault. For case D, where both P score and M score are less than 100%, we see non-empty TPSF and TFSP. One possible explanation is bridging fault. Now we will show an example for case C. Suppose there is T1 stuck open 4 in this circuit, which means that transistor T1 can never be turned on. If we apply test patterns 01, 01, and 00, this circuit will fail the test because the good output is 1 for the second pattern, but faulty output is 0 for the second pattern. This is a TFSF for A stuck at 1, 4. However, if we apply the sequence 0, 0, 0, 1, and 1, 1, because of the parasitic capacitance at the output, the faulty output here still remain output 1, so the fault cannot be detected on the tester. This corresponds to a TPSF. From this figure, we can see that TPSF is non-empty. This is a particular example for case C. This page shows an example for case D. Consider a AB wire end fault. This fault would sometimes behave like A stuck at 04, but sometimes behave like B stuck at 04. This table shows possible combination of the values of A and B. When the good values of A and B are both 0, the circuit will pass the test. This corresponds to TPSP for A stuck at 04. When A is 1 and B is 0, this circuit could fail the test because the value of A and B are not the same. This would correspond to TFSF for A stuck at 04. However, when A is 0 but B is 1, this circuit could fail the test because the value of A and B are not the same. But this would correspond to a TFSP for A stuck at 04. Because the value of A is 0, in simulation, this can never cause a failure. When both A and B are 1, the circuit will pass the test. However, for A stuck at 04, this could correspond to a TPSF. As we can see from this picture, the simulation failure of A stuck at 04 and the test failure are not the same. This is the same for B stuck at 04. This fault is very difficult to diagnose using only single stuck at fault information. So we would need physical aware diagnosis for better diagnosis result. The details of physical aware diagnosis is out of the scope of this talk. Please refer to other papers for more details. This slide compares the pros and cons of static cause-effect diagnosis. The advantage of static cause-effect diagnosis is that the algorithm is very simple, and the diagnosis can be done very quickly once the fault dictionary is obtained. So this is useful when the test failure data is very large. However, static cause-effect diagnosis requires a very long runtime to generate the fault dictionary. What is worse, the fault dictionary size is very large to be stored in practice. One solution is that we can perform for dictionary compression. However, the diagnosis accuracy or resolution can be degraded due to the information loss. This is a typical trade-off between space and the diagnosis results. This slide shows one example for dictionary compression. Suppose this is our original for dictionary. We can remove the failing pin information. That means no matter output 7 or 8 fail the test, we will put an X here. By doing this, we can remove the dimension of failing pins. Or even we can keep only the first failing pattern information. For example, we only keep the first failing pattern and remove the other failing pattern. This is because on the tester, we typically keep only the first failing information to save the storage space. To save the test time, a CUT will be aborted when we have the first failure. This is called abort on first failure. So if we remove the second failing pattern information, we can save some storage space. In summary, in this talk, we have introduced the static cause-effect diagnosis. After the fault simulation, we create a fault dictionary. Based on the comparison result, we can have 4 outcomes, which are TFSF, TPSP, TFSP, and TPSF. We can calculate the diagnosis score, which measures the similarity between TF and the SF. There are many definitions of diagnosis scores, and we show 3 examples in this talk. When the dictionary size is very large, we can compress the fault dictionary at the cost of diagnosis resolution degradation. This is the end of this talk. Thank you.